Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at first principles. So this was the idea. We want to find the gradient of this function here at this point, and I'll just call the x value x. So we started off looking at secants like this. Hit the graph twice. But this is not a good representation of the graph around the point that I marked in green. This secant's not even going in the same direction as the curve at that point. What we saw was if we make these secants closer and closer together, they start to be a better approximation of the curve at that point. So this was our formula for the gradient of the secant. It involves 2 points, one of them at x, one of them at x plus h. So what we want is these 2 points to be as close as possible together. Now h, which equals delta x, is the distance between those two x values. So because we want them to be as close as possible together, the way we write that mathematically is this: the limit as h approaches 0. What we're doing is we're taking 2 points that are as close as possible together and drawing a secant through them. But of course, as the points become closer and closer together, the secant becomes a tangent. It becomes a line that hits the graph only once. See, what we're doing, if we want to find the derivative, we want to find the rate of change of this function at this point, we're essentially finding the gradient of the tangent. The tangent just hits the graph at that one point in the neighborhood, and it goes in the same direction. Now, I just want to make a quick point. A tangent can actually intersect a graph more than once. So the tangent of the graph at this point actually does hit the graph more than once, but it hits it only once in this neighborhood. This blue line is the tangent to the red curve at this point. So this here is what we call the derivative, and we usually denote it as f dash or f prime of x. So we calculate the derivative according to this function here. It is just the gradient of the secant that goes through 2 points of the curve, but we want those points as close as possible together. So it becomes the gradient of a tangent. Okay, so how would we differentiate, that is, find the derivative of fx equals x to the power of 5 plus 1? Well, we're just going to use this formula here. So it's always limit as h approaches 0. Now, what would be f of x plus h? Well, if f of x is x to the power of 5 plus 1, f of x plus h is equal to, every time where you see an x, I'm just going to replace it with x plus h. So the way that we expand these brackets, we use Pascal's triangle if you need. So this is what we get from x plus h to the power of 5, and then we have our plus 1 on the end. So that's f of x plus h. Now we need to minus f of x. So when you're minusing f of x, make sure you use brackets, and that's all divided by h. Now, a few things here will cancel out. X to the power of 5 minus x to the power of 5 is nothing. 1 minus 1 is nothing. All of that cancels out. Now, what we saw when we were doing limits, when we have a situation like this, we can't substitute h as 0 because we'd be dividing 0. So what we're going to do is we're going to take each term one by one and divide by h. So 5x to the power of 4 divided by h, and 10x cubed h squared divided by h, and so on. Now we have an equivalent expression into which we can substitute h for 0. Now remember, x doesn't depend on h, so we leave all the x's alone. So we end up just with 5x to the power of 4. This will become 0, 0, 0, 0. It's just 5x to the power of 4. So the gradient of this function is 5x to the power of 4. That's f dash of x. So we can substitute into this any x value to find the gradient of the tangent at that point. For example, this curve goes through the point 1, 2. So if I want to find the gradient at that point, I just substitute x for 1 into the derivative. It'll be 5 times 1 to the power of 4, or 5. That will be the gradient of the tangent to this curve at the point x equals 1. All right, let's look at some other examples. So let's differentiate fx equals 1 over x using this formula. So to find the derivative, it's always going to be limit as h approaches 0. So f of x plus h means you take your function 1 over x, and everywhere you see an x, replace it with x plus h. Then minus f of x, all divided by h. Now, once again, we can't substitute h for 0. We would get a divide by 0 error. So we're going to simplify this fraction here. We're going to combine these two into a single fraction. Means I have to times top and bottom by x, top and bottom by x plus h. So combining these two into a single fraction, I still can't substitute h for 0. I'd get a divide by 0 error. But what happens is I can simplify this top here. X minus x is 0. I'm just left with negative h on top, and then I have the rest. So here I have h on top and the bottom. They can actually cancel out. So I'm actually left with just minus 1 on the top. So now I have a situation where I'm taking the limit as h approaches 0 of minus 1 over x times x plus h. I can substitute h for 0 here because that means the bottom will just become x times x, or x squared. So the final answer is negative 1 over x squared. That is the gradient function of this function here. So if I want to know the gradient of the tangent to this curve at any point, I just substitute the x value of that point into here, and that number will be the gradient of the tangent. So let's look at fx equals sine x. So the derivative is f of x plus h, so I'm just going to replace x with x plus h, minus the original function fx over h, take the limit as h approaches 0. So in order to simplify this, because again I can't substitute h for 0, I'm going to use the angle sum formula for sine. So it's sine of the first cos of the second plus sine of the second cos of the first. And I still have my original fx there, divided by h, taking the limit as h approaches 0. I then split up the fraction. So these 2 over h were into one fraction, and I factorized the top, and then this became another fraction. Now, we learned when we were doing limits that these two actually have very specific values. See, it turns out the limit as h approaches 0 of cos h minus 1 over h is 0. So that means that this just becomes sine x times 0, which is obviously just 0. So what about this one here? Well, we learned when we were doing limits that the limit as h approaches 0 of sine h over h is 1. So this is just going to become 1 times cos of x. Now note, what I said about these limits only works if the arguments are all in radians. So x, h, they must be in radians. So the final derivative is 0 plus 1 cos x, which is cos x. The derivative of sine x is cos x. All right, let's look now at one more example. So we're going to look at fx equals e to the power of x. E is Euler's number 2.71828. It is irrational, so decimal goes forever with no pattern. So what we're going to do is we're going to use the same formula we've been using in all the other examples. So the derivative is going to be, again, the limit as h approaches 0. So we start off with f of x plus h. So I'm going to replace x in this function with x plus h. So I get e to the power of x plus h minus f of x, which is e to the x over h. Again, I cannot substitute h for 0. That would give a division by 0 error. So what we're going to do is algebraically manipulate this. Now note, e to the x plus h is e to the x times e to the power of h. So I can actually take out a factor of e to the power of x, and I'm left with this. So we learned when we're doing limits, this limit here is actually equal to 1. You can use your calculator for that. Choose smaller and smaller values for h. As h approaches 0, e to the power of h minus 1 over h is equal to 1. So this is just going to be equal to e to the power of x times 1, because of course e to the x has nothing to do with h. So it turns out the derivative of e to the x is actually itself e to the power of x. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.